Hello there, and welcome to Sleepy Science Vault. There is a layer around our planet that most of us never think about, and yet, without it, none of us would be here at all. We call it the atmosphere. But that word is almost too small for what it actually does. It is Earth's invisible shield, a quiet, unseen guardian that has been protecting life on this planet since long before the first human ever looked up at the sky and wondered what was out there. Tonight, we are going to explore that shield. Slowly, gently, one fact at a time. Not to overwhelm you, but to help your mind settle into something vast and calming, the story of the air above us, and the silent protection it offers every single moment of your life. So let your body settle in wherever you are right now. There is nothing you need to do, nothing you need to figure out. Just listen, and let the story of our planet's invisible armor carry you gently toward rest. Let's begin. High above the ground you are standing or lying on right now, there is a layer of gases wrapped gently around the Earth. We call it the atmosphere, and in many ways, it behaves like a blanket. Not a blanket made of fabric or wool, but one made of air itself, a blanket of gases that traps just enough warmth to keep our planet livable. Without this atmospheric blanket, the heat from the sun would simply escape back into space almost as quickly as it arrived. Earth would freeze at night and scorch by day, with no gentle buffer in between. But because this layer surrounds us, because it holds on to warmth the way a blanket holds on to body heat, life became possible here. Not just possible, but abundant. Forests, oceans, deserts, mountains, and every living creature you have ever seen or heard of, all of it exists because this thin layer of gas found a way to keep our world within a livable range of temperature. It is easy to take a blanket for granted when you are wrapped inside one. And in many ways, we do exactly that with our atmosphere. We rarely notice it, because it does its work quietly, continuously, without asking for anything in return. And here is something remarkable: when you consider the size of our planet, this protective blanket is almost impossibly thin. Earth is enormous. Its diameter stretches across more than 12,000 kilometers. And yet the atmosphere, the very thing that shields us from the harshness of space, does most of its critical work in a layer that is almost delicate by comparison. If you could shrink the Earth down to the size of an apple, the breathable atmosphere would be thinner than the apple's skin. It is a strange thought, isn't it, that something so thin could be doing something so important? We often assume that protection requires bulk, thickness, mass. But Earth's atmosphere teaches us something different. It teaches us that a layer does not need to be large to be powerful. It only needs to be positioned exactly right, layered with the right gases, held in place by the right forces. And that thinness becomes even more striking when we look at actual numbers. In many places around the world, the breathable, life-supporting portion of our atmosphere is only about 5 to 9 miles thick. 5 to 9 miles, think about how short that distance really is. It's a distance many people could drive in just a few minutes. And yet within that narrow band of sky, an entire world of weather unfolds. Clouds drift. Storms gather. Birds soar. Rain falls. Almost everything we associate with the sky happens within this surprisingly slim ribbon of atmosphere hugging the surface of our planet. Beyond that, the air continues, but it thins dramatically, stretching upward in ways that become less and less familiar to us. It's worth pausing here for a moment, just to imagine it. A layer only a few miles thick, wrapped around a sphere thousands of miles wide, quietly making everything possible. So how does something so thin manage to stay in place at all? Why doesn't it simply drift away into the emptiness of space? The answer is gravity. Earth's gravity is constantly, gently pulling everything toward its center, including the gases that make up our atmosphere. This invisible pull is what keeps the air from floating off into the void. It holds the atmosphere close, like a hand cupped gently around a flame, keeping it steady, keeping it from scattering into darkness. This is one of those forces we never see, never feel directly, and yet rely on with every breath. Gravity doesn't announce itself. It doesn't ask for credit. It simply works, quietly and continuously, holding our protective shield firmly in place around the Earth, asking nothing, offering everything. And yet, even though gravity holds the atmosphere close, it doesn't create anything like a solid, sharp edge. There is no dramatic wall marking where sky ends and space begins. Instead, the atmosphere fades. It thins gradually, slowly loosening its grip the farther it stretches from the surface, until eventually, the space between air molecules becomes so vast that it starts to resemble the emptiness of space itself. There is no clean line. No sudden boundary. Just a long, gentle transition, air becoming thinner and thinner, quieter and quieter, until it eventually dissolves into the silence of the cosmos. It's a soft way for a shield to end, isn't it? Not with a wall, but with a whisper. This gradual fading is part of why scientists themselves don't always agree on exactly where the atmosphere ends. Because there is no dramatic boundary to point to, no clear line separating here from there, researchers have had to choose different definitions depending on what they are measuring. Some look at where air becomes too thin to support certain physical processes. Others look at where the effects of Earth's gravity and magnetic field begin to compete with the pull of the sun. There is something comforting, in a way, about a natural feature that resists being neatly defined. Not everything in nature needs a hard edge. Sometimes protection simply fades outward, slowly, endlessly, without needing a boundary at all. But even without an exact line, scientists have found ways to describe just how far this atmospheric shield truly reaches. And the distance may surprise you. Earth's atmosphere doesn't stop just a few miles above our heads. It doesn't stop at the clouds, or even far above where airplanes fly. It continues stretching upward, farther and farther, all the way out to roughly 10,000 kilometers above the surface before it fully fades into the vacuum of space. 10,000 kilometers. That is a distance almost impossible to picture from the ground. It reaches out into a region far beyond what we normally think of as sky, extending into a thin, ghostly presence that lingers for an enormous distance before finally releasing its hold. This outermost region, the far, faint edge of our atmosphere, is called the exosphere. It is here, in this final stretch, that individual particles drift so far apart that they barely interact with one another anymore. It is quiet out there, sparse, almost dreamlike. And yet, this too is still technically Earth. Still part of our shield. Still, in some faint and quiet way, connected to the world beneath it. Knowing this changes the way we might picture our planet, doesn't it? We often imagine Earth as a blue and green sphere, with a thin visible haze of atmosphere hugging its edges in photographs from space. But in truth, Earth's real shape, its full protective presence, stretches vastly farther than the eye can see. Our world is larger, more expansive, more quietly powerful than it first appears. So as we come to the end of this first gentle stretch of facts, take a moment to imagine your place within all of this, beneath a shield so thin it could be mistaken for nothing at all, yet so vast it stretches thousands of kilometers into the dark, held together not by walls, but by gravity, not by sharp edges, but by slow, patient fading. There's still so much more to uncover about this invisible protector, how it moves, how it shifts, how it quietly deflects the dangers of space above us. In the next part of our journey, we'll continue drifting upward and outward, discovering more about the delicate layers that make up this remarkable shield surrounding our world. For now, just rest here, in this thought, wrapped, gently and completely, in a blanket of air that has been protecting life on Earth since the very beginning. We left off drifting through that faint, quiet edge where Earth's atmosphere finally dissolves into space. But now let's turn around, and travel back down, toward the surface, to understand how this shield is actually built. Because it isn't one single, uniform layer. It's more like a tower of distinct regions, each one different from the last, each one playing its own particular role. Scientists divide the atmosphere into 5 major layers, and they do this based primarily on temperature. As you move upward through the atmosphere, the temperature doesn't just steadily drop the way you might expect. It rises and falls in a pattern, almost like gentle waves, and each of these temperature patterns marks the boundary of a new layer. Closest to us is the troposphere, the layer we live in, breathe in, and experience as weather. Above that comes the stratosphere, home to the ozone layer we'll explore more later. Then the mesosphere, where meteors burn up in brief streaks of light. Beyond that, the thermosphere, where temperatures can climb to startling extremes even though the air is so thin it would feel freezing to human skin. And finally, the exosphere, that far away, fading edge we just described, where the atmosphere quietly releases its hold and space truly begins. 5 layers. 5 distinct personalities, if you will, stacked one atop another, each shaped by its own physics, its own behavior, its own relationship with the sun. And what's remarkable is how differently each layer behaves, despite being made of the same basic ingredients. The layer nearest to us churns with clouds, wind, and storms, constantly active, constantly changing. But climb higher, into the layers where satellites orbit, and the atmosphere becomes an entirely different environment, calm in some ways, extreme in others, shaped by radiation rather than rainfall. It's a bit like a building with several floors, each designed for a completely different purpose. The ground floor bustles with life and motion. But climb higher, and each new floor reveals a quieter, stranger version of the same structure, still part of the same building, yet worlds apart in character. Weather forms in the lowest of these floors. Satellites orbit in the higher ones. Between them lies a series of transitions, quiet thresholds where one atmospheric world gives way to the next. Now, let's shift focus for a moment, away from these grand layers, and towards something more intimate, the actual ingredients that make up the very air filling your lungs right now. You might assume the air around us is mostly oxygen, since that's the gas we so often associate with breathing and life. But that assumption would be incorrect. The atmosphere is composed mostly of nitrogen. In fact, nitrogen makes up the overwhelming majority of the air surrounding us, an invisible, odorless gas that quietly fills nearly 4/5 of every breath we take, without asking for any recognition at all. Oxygen, meanwhile, the gas so essential to human life, makes up a much smaller portion than most people realize. To be precise, Earth's atmosphere is composed of roughly 78% nitrogen, and only about 21% oxygen. The remaining sliver, just around 1%, is made up of a delicate mixture of other gases. Isn't that a curious thing to sit with? The gas most associated with survival, with breath, with life itself, is actually the minority ingredient in the air around us. Nitrogen, the quiet, background gas, is actually the dominant presence, filling the sky in vast, invisible abundance, while oxygen plays a smaller, though undeniably vital, supporting role. It's a reminder that importance doesn't always align with quantity. Sometimes the most essential elements exist in smaller amounts, carefully balanced within something much larger. In that final 1%, that thin remaining slice of atmosphere, is where things become especially delicate. Within that small percentage live gases like argon, carbon dioxide, methane, water vapor, and neon. Each of these exists only in trace amounts, barely perceptible fractions of the whole. And yet, despite their scarcity, they carry enormous influence over our planet's climate, weather, and even the possibility of life itself. Carbon dioxide, though tiny in proportion, plays a crucial role in trapping heat and helping regulate Earth's temperature. Water vapor, similarly minor in overall percentage, is responsible for clouds, rainfall, and the entire water cycle that sustains ecosystems around the world. Even methane, present in only the faintest traces, has an outsized influence on the atmosphere's warmth. It's almost poetic, in a way, how such a small sliver of gases can carry such enormous responsibility. As though nature designed the atmosphere not through overwhelming abundance, but through careful, precise balance. Argon deserves its own quiet moment of attention here too. Argon is what's known as a noble gas, meaning it doesn't easily react with other elements. It simply exists, drifting quietly among the nitrogen and oxygen, present in a small but stable amount. And though it doesn't sustain life the way oxygen does, or trap heat the way carbon dioxide does, its steady, unreactive presence helps maintain the overall balance of our air. Think of argon as a quiet stabilizer, not the star of the story, but a steady, dependable presence, holding its place within the mixture, contributing to an atmosphere that remains, on the whole, remarkably consistent and life-sustaining. There's something calming, isn't there, In imagining these gases drifting together in such careful proportion, nitrogen offering its vast, quiet abundance, oxygen offering its life-giving presence, argon offering quiet stability, all blending together into something breathable, something livable, something that makes every single breath you take possible. And nestled even further into that thin 1%, we find gases so faint they almost seem symbolic more than functional: helium and neon. These two gases exist only in the smallest of traces within our atmosphere. Helium, so light that much of it eventually drifts upward and escapes into space over long periods of time. Neon, quiet and inert, drifting invisibly among the more abundant gases surrounding it. Neither helium nor neon plays a major role in sustaining life directly. And yet, they are still there, present in every breath, in every gust of wind, in every quiet expanse of open sky above us. Tiny threads woven into the larger tapestry of Earth's air. It's a gentle reminder that even the smallest, faintest elements still belong, still matter, still hold their small place within something much larger than themselves. And when we step back and look at this entire mixture together, the abundant nitrogen, the essential oxygen, the stabilizing argon, the delicate trace gases, what emerges is something extraordinarily well suited for life. Not because any single gas is perfect on its own, but because of how precisely they come together. This particular blend allows humans and animals to breathe steadily. It allows plants to draw on carbon dioxide and release oxygen in return, creating a quiet, continuous exchange between living things and the air around them. It allows fires to burn at a controlled rate, rather than igniting uncontrollably. It allows weather patterns to form gently, rather than violently. In many ways, the atmosphere is a kind of quiet negotiation, an ongoing balance between different gases, different proportions, different roles, all working together, without conflict, to create an environment where life can not only survive, but truly flourish. And as we continue drifting through this story of Earth's invisible shield, layer by layer, breath by breath, we'll soon move even closer to one of its most remarkable regions, the delicate, protective layer high above us that quietly filters the sun's harshest rays before they ever reach the surface. For now, let this thought settle gently in your mind, that every breath you've taken tonight, every quiet inhale and exhale, has been made possible by an intricate, invisible balance stretching far above you, a balance built not from abundance alone, but from precision, layer upon layer, gas upon gas, quietly sustaining life above the surface of our world. Let's return now to that quiet balance of gases we spoke of before, and look more closely at what it actually does for the living things sharing this planet with us. Because chemistry alone doesn't explain why life exists here. What matters is what that chemistry provides, how it reaches into the lungs of every creature, into the leaves of every plant, into the very possibility of a living, breathing world. And it begins with something so simple, so automatic, that we rarely stop to appreciate it. Every breath you take draws oxygen from the air around you. That oxygen travels into your lungs, into your bloodstream, into every cell in your body, quietly fueling the processes that keep you alive. Animals everywhere, birds resting in trees, whales moving through deep water, small creatures burrowed beneath the soil, all depend on this same invisible resource, drawn continuously from the atmosphere above them. It's such a constant, automatic act that we hardly notice it happening. And yet, this simple exchange, air moving in, oxygen absorbed, breath moving out, is one of the most essential relationships between life and the sky above it. But the atmosphere doesn't only give to the animal world. It offers something just as vital to the plants that share this planet with us. Where animals draw on oxygen, plants draw on carbon dioxide. Through the quiet, patient process of photosynthesis, plants take that carbon dioxide from the air and, with the help of sunlight, transform it into energy, releasing oxygen back into the atmosphere in return. It's a kind of quiet partnership, isn't it? Animals breathing out carbon dioxide. Plants breathing it in. Plants releasing oxygen. Animals breathing it in return. A slow, continuous cycle, repeating endlessly, day after day, season after season, connecting every living thing to every other living thing through nothing more than the air passing between them. There is something deeply peaceful about imagining this cycle in motion right now, even as you rest. Somewhere, a leaf is quietly absorbing carbon dioxide. Somewhere, a breath is being taken. Somewhere, oxygen is being released back into the open sky. All of it happening softly, continuously, without needing our attention at all. And this careful balance of gases does something else, something perhaps unexpected. It keeps our planet from becoming dangerously flammable. Oxygen, while essential for life, is also a gas that fuels fire. If the atmosphere contained a much higher concentration of oxygen, the entire surface of our planet would become extraordinarily vulnerable to rapid, uncontrollable burning. Forests could ignite far more easily. Fires could spread with terrifying speed. But nitrogen, that quiet, abundant gas we spoke of earlier, helps prevent this. By diluting the oxygen within our air, nitrogen reduces the risk of rapid combustion, keeping fire a rare and containable event rather than a constant, uncontrollable threat. It's a subtle kind of protection, isn't it? Not a shield against something falling from the sky, but a shield built directly into the chemistry of the air itself, a careful dilution that keeps our world from becoming far too dangerous a place to live. This same delicate mixture, this same careful balance between gases, is part of what keeps Earth's surface stable enough for something else essential to life: liquid water. Water is remarkably particular about the conditions it needs to remain in liquid form. Too cold, and it freezes into ice. Too hot, and it evaporates into vapor. But here on Earth, thanks to the stabilizing presence of our atmosphere, temperatures remain within a range that allows water to exist as liquid across much of the planet's surface, filling oceans, rivers, and lakes, and making life as we know it possible. Without this atmospheric stability, water could not remain liquid the way it does. Life dependent on flowing rivers, rainfall, and open oceans simply would not exist. The atmosphere, in its quiet way, holds open a narrow, precious window, a window of temperature and pressure just wide enough for water to remain in its most life-giving form. And speaking of water, there is a surprising detail about how much of it drifts, invisibly, through the air above us right now. Scientists estimate that if all the water vapor currently suspended in Earth's atmosphere were to condense at once, It would be enough to cover the entire surface of the planet in roughly 1 inch of rain. Just imagine that for a moment. An invisible layer of moisture, drifting unseen through the sky above every ocean, every continent, every quiet corner of the world, enough, if gathered together, to blanket the whole earth in a gentle inch of rainfall. We don't see this water vapor. We don't feel its full presence unless humidity rises or clouds gather overhead. But it's there, always, floating quietly through the atmosphere, waiting for the right conditions to gather, cool, and fall gently back to the surface below. This vast, invisible reservoir of water vapor does more than simply exist in the background. It actively supports the formation of clouds and the arrival of rain. As water vapor rises and cools within the atmosphere, it begins to condense around tiny particles suspended in the air, forming the clouds we so often watch drift lazily across the sky. Within these clouds, tiny droplets of water gather and grow, until eventually, they become heavy enough to fall as rain, or in colder regions, as snow. It's a slow, patient process, hidden mostly from view until the final moment it becomes visible, clouds forming, darkening, gathering weight, and finally releasing their contents gently back to the earth below. This entire process is part of something much larger, the water cycle, a continuous, endless movement of water through evaporation, cloud formation, and precipitation. Water evaporates from oceans, lakes, and rivers, rising invisibly into the atmosphere as vapor. There, it cools, condenses, and forms clouds. Eventually, that moisture falls back to the surface as rain or snow, replenishing rivers, lakes, and oceans once again, only to begin the entire process anew. It is one of the quietest, most patient cycles on our planet, water rising, cooling, gathering, falling, and rising once more, endlessly repeating itself across the surface of the earth. And this same reservoir of atmospheric moisture plays a critical role in supporting rainfall and weather systems around the globe. Without sufficient water vapor drifting through the atmosphere, rain simply couldn't form the way it does. Entire ecosystems dependent on seasonal rainfall would struggle to survive. Rivers would run dry. Agriculture, wildlife, and countless delicate ecosystems all rely, in one way or another, on this quiet, continuous supply of atmospheric moisture, gathering and falling in patterns that have shaped life on Earth for millions of years. But water vapor alone doesn't create the full complexity of weather and climate we experience. Something else is needed: movement. This is where atmospheric circulation comes into the story. Warm air rises near the equator, where sunlight strikes the Earth most directly. As this warm air rises, it begins a long, slow journey, drifting toward the poles, cooling gradually as it travels. Eventually, this cooler air sinks back downward, only to be drawn once again toward the equator, continuing an enormous, continuous loop of motion that circles the entire planet. This constant movement of air does more than simply create wind. It redistributes heat and moisture across the globe, carrying warmth toward colder regions and moisture toward drier ones. It is this circulation that helps shape our planet's climate zones: the humid tropics, the dry deserts, the temperate regions in between, each one influenced by these vast, continuous currents of moving air. It's a beautifully vast system, isn't it, when you really sit with it? Heat and moisture, constantly moving, constantly redistributing themselves across the surface of our planet, shaping deserts and rainforests, gentle breezes and powerful storms, all part of one continuous, atmospheric rhythm. And so, as we come to the end of this section of our journey, take a quiet moment to consider everything happening above you right now, even as you rest. Oxygen quietly nourishing the animal world. Carbon dioxide quietly feeding the plants. Nitrogen gently tempering the risk of fire. Water vapor drifting invisibly, waiting to become rain. And vast currents of moving air, carrying warmth and moisture across the entire planet, shaping the climate of every place you have ever known. All of it happening quietly, continuously, invisibly, high above the surface of the world, in the delicate, endlessly balanced layer we call Earth's atmosphere. In the next part of our journey, we'll rise even higher, into the layers where this atmosphere begins to reveal its more protective, more dramatic qualities, shielding us not just from fire or flood, but from the far harsher dangers drifting through space itself. For now, rest here a while longer, beneath a sky quietly at work, carrying warmth, moisture, and life itself, gently across the surface of our world. We spoke earlier about heat and moisture moving across the planet in great, slow currents. But there's another kind of warmth we haven't fully explored yet, one that doesn't come from circulation, but from something far more delicate. A kind of trapping. A kind of holding on. It's called the greenhouse effect, and it may be one of the most important reasons Earth feels like home at all. Here is how it works. Sunlight travels down through the atmosphere and warms the surface of the Earth during the day. But once night falls, that same surface begins to release its stored heat back upward, back toward space. And this is where certain gases in our atmosphere step quietly into the story. These gases don't let all of that heat simply escape. Instead, they capture a portion of it, holding it close to the surface, keeping the planet from losing its warmth too quickly once the sun goes down. It's a gentle kind of retention, not a complete seal, but enough of a hold to keep nighttime from becoming unbearably cold. Without this effect, the temperature difference between day and night would be far more extreme than anything we currently experience. Think of it almost like a thin blanket draped loosely over the Earth each evening, not thick enough to trap all the warmth, but just enough to soften the transition into darkness. And it isn't only about surviving the night. This same heat-trapping quality plays a much larger role in shaping the overall temperature of our planet. Certain gases within the atmosphere work quietly, continuously, to help keep Earth's surface at an average temperature suitable for life. Not too cold to freeze the ocean solid. Not too hot to boil away the moisture that sustains ecosystems. Just balanced. A livable range, sustained gently over long periods of time by an invisible process happening far above our heads. It's worth pausing on that word, livable. Because livability isn't something that happens by accident. It's the result of an intricate, ongoing balance, one shaped by the very air surrounding us, holding just enough warmth in place to make life possible across the surface of the world. And when we imagine what Earth might look like without this quiet warming effect, the picture becomes considerably harsher. Without the heat-trapping influence of these atmospheric gases, our planet would be significantly colder than it is today. Not colder in a mild, comfortable way, but colder in a way that would make life, as we currently understand it, extraordinarily difficult to sustain. Oceans might freeze more extensively. Growing seasons could shrink. Entire ecosystems dependent on stable, moderate temperatures might struggle to survive at all. It's a strange thing to consider, how much we owe to gases we cannot see, holding on to warmth we rarely think about, simply so that life can continue unfolding gently across the surface of our world. In fact, without this atmospheric warming, Earth would likely resemble something closer to an icy world, a planet locked in far colder, harsher conditions than the one we know and often take for granted. This is perhaps one of the most striking truths about our atmosphere. It isn't simply protecting us from external threats, like harmful radiation or extreme cold. It is actively shaping the very climate that allows life to exist here at all, quietly working to keep Earth from drifting into a far more frozen, far more inhospitable version of itself. Two gases in particular play a leading role in this warming process: carbon dioxide and methane. Though both exist only in small proportions within the atmosphere, as we discussed earlier, their influence on temperature is remarkably significant. Within the troposphere, the lowest layer of our atmosphere, these gases help trap just enough heat to keep the surface of our planet within a range comfortable enough to sustain forests, oceans, and every living creature dependent on them. It's another quiet reminder that scale and impact don't always align. These gases exist in only the smallest of quantities, and yet their warming influence touches nearly every living thing on Earth. But this heat-trapping effect doesn't only protect us from extreme cold. It also softens the dramatic swings between day and night, ensuring temperatures don't shift too violently as the sun rises and sets. On a planet without this stabilizing atmospheric layer, daytime heat might escape almost immediately once the sun disappeared, causing nighttime temperatures to plummet dramatically. But because our atmosphere holds a portion of that heat in place, the transition between day and night becomes far gentler, a slow cooling, rather than a sudden, jarring drop. This is part of why life across our planet can adapt so steadily to daily cycles, rather than facing extreme, unpredictable temperature shifts every single day. The atmosphere smooths these transitions, offering a kind of thermal steadiness that living things have relied upon for countless generations. Now, let's shift our attention upward once more, beyond the troposphere, into a higher, quieter layer of the sky, the stratosphere. Because it's here, in this elevated region, that one of the atmosphere's most protective features resides. The ozone layer. High above the clouds, within the stratosphere, a thin and delicate layer of ozone gas stretches around the planet. And its role is remarkable. This layer absorbs much of the sun's ultraviolet radiation before it ever has the chance to reach the surface below. Ultraviolet radiation, though invisible to our eyes, carries significant energy capable of damaging living tissue if left unchecked. But the ozone layer, quietly positioned high above us, intercepts much of this radiation, absorbing it into itself before it can reach the delicate life thriving on the surface far beneath. It's almost like an invisible curtain, drawn gently across the upper atmosphere, not blocking sunlight entirely, but filtering out its harshest, most damaging components before they ever reach the ground. This protective quality of the ozone layer becomes especially significant when we consider just how much ultraviolet radiation it manages to block. A substantial portion of the sun's UV rays are absorbed within this single, delicate layer, drastically reducing the amount that ultimately reaches Earth's surface. Without this filtering effect, the intensity of UV exposure reaching living organisms would be far greater, potentially far more damaging to skin, eyes, and other sensitive biological tissues. But because of the ozone layer's quiet, continuous presence, much of that harshness is absorbed high above us, long before it ever touches the world below. And this protection reaches even deeper than the surface of our skin. It reaches into the very building blocks of life itself. Ultraviolet radiation, when left unfiltered, has the potential to damage DNA, the delicate genetic material found within nearly every living cell. This kind of damage can disrupt the normal functioning of cells, and in some cases, contribute to serious, long-term harm. By absorbing much of this radiation before it reaches the surface, the ozone layer plays a critical role in protecting DNA from this kind of damage, offering a kind of biological shielding that operates high above us, invisible, yet profoundly important. It's worth sitting with that thought for a moment. Somewhere, high above the clouds, in a layer of the sky most of us will never see or think about, an invisible shield is quietly protecting the genetic code within your own cells, working continuously, silently, without ever asking for recognition. This same protective quality extends to biomolecules more broadly, the delicate proteins, enzymes, and structures that allow living cells to function properly. Excessive UV exposure has the potential to damage these molecules as well, disrupting processes essential to life at the cellular level. But thanks to the ozone layer's quiet filtering, much of this potential damage is prevented before it can occur. Cells continue functioning as they should. Biological processes continue unfolding steadily, undisturbed by the harsher radiation drifting just beyond our atmosphere's protective reach. It's remarkable, isn't it, to realize how many layers of protection exist simply so that life can continue quietly, safely, undisturbed. Warmth held gently in place by greenhouse gases. Temperature extremes soften between day and night. Harmful radiation absorbed high above us by a delicate layer of ozone, shielding both skin and DNA from unnecessary harm. None of it visible. None of it something we consciously notice as we go about our days, or as we rest quietly through the night. And yet, all of it working together, continuously, invisibly, high above the surface of our world, holding warmth in place, softening extremes, and filtering away danger before it ever reaches us. In the next part of our journey, we'll continue rising through this remarkable shield, uncovering even more of the quiet, protective forces that make life on Earth possible, forces working high above us, every moment, whether we are awake to notice them or not. For now, let yourself rest a little longer beneath this invisible protection, this vast, quiet shield of warmth and filtration, stretching gently above the surface of the world, keeping it safe, night after night, breath after breath. We spoke of the ozone layer as a quiet filter, working high above us to absorb the sun's harshest ultraviolet light. but its importance reaches even further than we've described so far. In many ways, this delicate layer is one of the central reasons life on Earth's surface is possible at all. Without it, the intensity of ultraviolet radiation reaching the ground would be dramatically higher, enough to threaten the survival of countless organisms, from the smallest microscopic life to the largest and most complex creatures walking, swimming, or flying across our planet. The ozone layer doesn't simply reduce discomfort. It makes survival itself more achievable. It stands as one of the atmosphere's quiet cornerstones, a single, thin layer, high above the clouds, holding back a force that could otherwise reshape life on Earth entirely. And yet, ultraviolet radiation is only one part of a much larger story. The sun sends far more than just UV rays toward our planet. It sends a constant stream of energy in many forms, and the atmosphere, in its entirety, plays a role in managing all of it. In fact, before sunlight ever reaches the surface beneath your feet, a significant portion of the sun's total energy has already been absorbed or reflected by the atmosphere itself. Clouds reflect some of it back into space. Gases absorb other portions, converting that energy into heat, or filtering it in ways that reduce its intensity by the time it finally reaches the ground. This means the sunlight you feel on your skin during the day, warm, gentle, familiar, is already a filtered, softened version of something far more intense. The atmosphere has already done a great deal of quiet work before that light ever touches you, absorbing and reflecting away a portion of the sun's raw power, leaving behind something far gentler, far more livable. It's worth imagining, just for a moment, the sheer scale of energy constantly arriving from the sun, and how much of it never actually reaches us at all, intercepted instead, high above, by layers of atmosphere working quietly on our behalf. Some of the most intense filtering of all happens far above the clouds, in a layer we touched on earlier, the thermosphere. This layer, positioned high above the mesosphere, plays a critical role in absorbing some of the sun's most energetic radiation, including high-energy X-rays and additional ultraviolet rays that manage to travel even further than the ozone layer alone can filter. The thermosphere intercepts much of this radiation before it has any chance of continuing downward toward the lower atmosphere, and eventually, the surface. It's almost like an outer layer of defense, positioned far above everything we experience as weather or sky, quietly absorbing some of the most energetic and potentially damaging radiation the sun sends our way. Interestingly, despite absorbing such high-energy radiation, the thermosphere itself experiences extreme temperature swings, sometimes reaching levels that sound almost unbelievable. And yet, because the air at that altitude is so thin, so sparse, those extreme temperatures wouldn't feel the way we might expect if we could somehow stand within that layer ourselves. It's a strange, distant world, intensely energetic, yet physically thin and quiet, absorbing danger long before it ever reaches the layers of atmosphere closer to home. But the sun isn't the only source of danger drifting through space. There is also a quieter, more constant threat: cosmic rays. These high-energy particles originate from far beyond our solar system, traveling vast distances through space before eventually reaching the outer edges of Earth's atmosphere. Some are remnants of distant exploding stars. Others come from sources scientists still don't fully understand. and if left completely unfiltered, these cosmic rays could pose significant risks to living organisms, potentially damaging cells and genetic material in ways similar to, or even more severe than, ultraviolet radiation. But Earth's atmosphere, along with its magnetic field working alongside it, helps intercept and deflect much of this cosmic radiation before it can reach the surface. Layer after layer, this vast atmospheric shield continues quietly absorbing, deflecting, and filtering away threats that arrive not just from our own sun, but from the depths of the galaxy itself. It's a humbling thought, isn't it, that some of the particles filtered away by our atmosphere may have traveled across unimaginable distances, only to be gently absorbed within the final stretch of their journey, just before reaching the world below. And it isn't only energy and radiation that the atmosphere protects us from. It also shields us from something far more physical, debris arriving from space itself. Countless small meteoroids, tiny fragments of rock and dust, remnants from comets, asteroids, and the early formation of our solar system, are constantly drifting through space, and many of them eventually cross paths with Earth. Left unprotected, these fragments could strike the surface with considerable force. But because of our atmosphere, most of them never make it that far. As these meteoroids enter the atmosphere at extremely high speeds, friction with the surrounding air causes them to heat up rapidly, so rapidly that most burn away entirely before ever reaching the ground. What we often witness is a brief, glowing streak of light in the night sky, commonly known as a shooting star, is usually the final, fleeting moment of a tiny meteoroid meeting its end high above us, harmlessly absorbed by the very shield protecting our planet. There is something quietly beautiful about that, isn't there? A fragment of ancient rock, perhaps older than Earth itself, traveling for millions of years through the emptiness of space, only to end its long journey in one brief, glowing streak of light, witnessed by someone gazing upward, making a quiet wish, never realizing just how much protection made that fleeting moment possible. This protective burning doesn't happen randomly throughout the atmosphere. It tends to occur most often within a specific layer, the mesosphere. Positioned between the stratosphere and the thermosphere, the mesosphere serves as a kind of mid-level shield, the region where the vast majority of meteors encounter enough atmospheric resistance to burn away completely. It's here, in this quiet, largely unseen layer, that so many of these small cosmic fragments meet their final moments, transformed from solid rock into brief streaks of light and heat, long before they ever pose any threat to the surface below. It's easy to imagine the mesosphere as a distant, empty space. But in truth, it's remarkably active, a constant, quiet battlefield of sorts, where incoming debris is met, resisted, and ultimately dissolved by the atmosphere's protective embrace. This same principle of atmospheric resistance, friction slowing and heating objects as they pass through the air, also plays a critical role much closer to human experience, particularly when spacecraft return home from beyond our planet. As spacecraft re-enter Earth's atmosphere after a journey through space, they travel at extraordinary speeds far greater than anything experienced in everyday life. Without some way to slow down, the impact of returning to Earth's surface would be far too violent to survive. But the atmosphere itself provides a natural braking mechanism. As a spacecraft descends through the upper layers of atmosphere, friction against the surrounding air gradually slows its speed, while simultaneously generating intense heat along its outer surface. This process, though extremely dramatic, allows spacecraft to reduce their velocity to a survivable level by the time they approach the ground, or in many cases, before they gently descend beneath parachutes toward a safe landing. It's remarkable to think that the very same atmospheric resistance responsible for burning away tiny meteoroids high above us also plays a role in safely guiding human-made spacecraft back home, the atmosphere acting not just as a barrier, but as a kind of gentle, if fiery, welcome home. And now, let's return, gently, to the layer closest to us, the one we spoke of earlier, at the very beginning of our journey, the troposphere. Of all the atmospheric layers we've explored so far, from the delicate stratosphere to the far-reaching thermosphere, the troposphere remains the densest of them all. It is here, within this closest, thickest layer of air, that we live our entire lives, walking, breathing, existing, without ever fully realizing just how much protective structure exists above us. This density isn't accidental. Because the troposphere sits closest to the surface, it experiences the strongest pull of Earth's gravity, drawing air molecules more tightly together than in any of the higher, thinner layers above. This is part of why weather, clouds, and nearly every atmospheric phenomenon we experience directly all take place within this single, relatively thin layer closest to the ground. Nearly every cloud you have ever seen drifting across the sky, every raindrop that has ever fallen against your skin, every gust of wind that has ever brushed against your face, all of it originates within the troposphere. It is, in many ways, the most familiar layer of our atmosphere, the one most directly connected to our daily lives, even as far more dramatic, far more protective processes continue quietly unfolding in the layers stretching high above it. So as we gather together everything explored in this section of our journey, take a moment to imagine the full scope of protection surrounding our planet. The ozone layer, absorbing harmful ultraviolet rays high above the clouds. Layers of atmosphere absorbing and reflecting the sun's energy before it reaches the surface. The thermosphere intercepting X-rays and additional radiation from deep within space. Cosmic rays, traveling unimaginable distances, gently deflected before ever reaching us. Countless meteoroids, burning quietly away within the mesosphere. Spacecraft, safely slowed by the very same atmospheric resistance. And finally, the dense, familiar troposphere, where weather forms, and where all of us live out our daily lives beneath this vast, quiet shield. Layer upon layer, each one distinct, each one essential, each one working together to create something far greater than the sum of its parts. A shield so vast it stretches thousands of kilometers into space, and yet so intimately connected to something as simple, as personal, as the breath moving gently in and out of your body right now. In the next part of our journey, we'll continue exploring even more remarkable qualities of this atmospheric shield, uncovering further layers of protection, further quiet wonders, hidden within the sky stretching endlessly above us. For now, let this thought settle gently within you, that above every quiet moment of rest, above every breath taken through the night, an entire, invisible fortress continues its patient work, absorbing, deflecting, filtering, and protecting, layer after layer, reaching from the ground beneath you, all the way out into the vast, silent edges of space. We ended our last stretch of facts resting on the troposphere, that dense and familiar layer closest to the ground. Let's linger there a little longer, because there is still so much to understand about this particular part of the sky, the part that touches our lives most directly, most personally, every single day. It makes sense, when you think about it, that this is where nearly all weather takes place. The troposphere is where life exists, where we walk, where we breathe, where forests grow and oceans stretch toward the horizon. And it is here, in this same layer, that the air is thick enough, dense enough, to hold the moisture needed for clouds to form and rain to fall. Higher layers of the atmosphere are simply too thin, too sparse, to support the kind of weather we experience here on the surface. So in many ways, it isn't a coincidence that weather and life share the same layer of sky. The very conditions that allow clouds to gather and rain to fall are closely connected to the conditions that allow life to flourish. Thick enough air. Enough moisture drifting quietly through it. Enough density to hold weather patterns together, rather than letting them dissolve into nothingness the way they might in the thinner air far above. Every cloud drifting lazily across a summer sky, every gentle rainfall on a quiet afternoon, every distant rumble of thunder rolling across the horizon, all of it takes place within this single, relatively narrow layer of atmosphere, closest to the world we call home. And it's worth remembering, all of it happens here, and nowhere else. Not in the stratosphere. Not in the mesosphere. All of Earth's clouds, all of its rain, all of its storms, gather and unfold within the troposphere alone. Even the name of this layer carries a quiet reflection of its nature. The word troposphere comes from a root meaning change, a fitting description for a layer defined almost entirely by constant motion and transformation. Clouds shift and reshape themselves by the hour. Winds rise and fall. Storms gather, unleash their energy, and dissipate, only for new patterns to begin forming shortly after. There is something almost poetic in that, a layer named quite literally for its tendency to change, existing as the one part of our atmosphere in constant, restless motion, while the higher layers stretch upward in comparative stillness and silence. It's a fitting reminder that where there is life, there is also change, and the troposphere, more than any other part of our atmosphere, embodies that truth completely. Now, let's turn towards something a little more structural, the physical density of this layer, and just how much of our atmosphere is actually contained within it. Though the troposphere occupies only a small portion of the atmosphere's overall height, stretching upward roughly 8 to 15 kilometers depending on location, it holds an extraordinary proportion of the atmosphere's total mass. In fact, most of the air surrounding our planet, most of the actual physical substance of the atmosphere, is packed into this relatively thin band closest to the surface. It's a striking thought, isn't it? All those higher layers we've explored, the stratosphere, the mesosphere, the thermosphere, stretching thousands of kilometers into space, together, they contain only a small fraction of the atmosphere's overall mass. The vast majority of it remains here, close to the ground, compressed by the pull of gravity into this dense, lower layer of sky. To put a number to it, scientists estimate that roughly 75 to 80% of the atmosphere's total mass exists within the troposphere alone. Nearly all of it, concentrated into this single, relatively narrow layer closest to us. This density isn't surprising when you consider the influence of gravity. Gravity pulls most strongly on the air closest to Earth's surface, compressing it more tightly than the air found in higher, more distant layers. As altitude increases, gravity's pull weakens slightly, and air molecules spread further apart, becoming thinner and thinner the higher you travel. This is why mountain climbers ascending to great heights often struggle to breathe as easily as they would at sea level. Even though they remain technically within the troposphere, the air at higher elevations is noticeably thinner, containing fewer oxygen molecules within each breath. It's a small, personal reminder of just how concentrated our atmosphere becomes near the surface, and how quickly that density fades as altitude increases. Interestingly, the troposphere itself isn't perfectly uniform in thickness across the globe. It varies depending on where you are standing on the planet. Near the equator, the troposphere reaches its greatest thickness, stretching higher into the sky than anywhere else on Earth. This happens because warm air, more abundant near the equator due to stronger, more direct sunlight, rises higher before eventually cooling and leveling off into the layer above. In these warmer regions, the troposphere can extend up to around 15 kilometers or more above the surface. But travel toward the poles, and the story changes. There, the troposphere becomes noticeably thinner, sometimes stretching upward only around 8 kilometers before giving way to the layer above. Colder air near the poles doesn't rise as high, resulting in a more compressed, shallower layer of troposphere compared to the equatorial regions. It's a quiet reflection of how deeply connected our atmosphere is to temperature itself. Warmth causing the sky to stretch higher above the equator. Cold causing it to settle closer to the surface near the poles. The very shape of this layer, shifting gently across the globe, shaped entirely by the sun's uneven warming of our planet. And within this variable, ever-changing layer, we also find a majority of something we touched on earlier, water vapor, along with fine particles of dust and volcanic ash. Because the troposphere holds the greatest density of air, and because it remains in such close contact with the surface of the Earth, it naturally accumulates the majority of atmospheric moisture, along with tiny airborne particles lifted from the ground below. Dust carried by wind. Ash released from distant volcanic eruptions. All of it tends to gather, drift, and circulate primarily within this lowest layer of the sky. This concentration of moisture, dust, and ash is part of why the troposphere remains the primary layer for cloud formation. Water vapor requires tiny particles to condense around, microscopic specks of dust, salt, or ash, drifting invisibly through the air, in order to begin forming the visible clouds we see gathering across the sky. Without these particles, water vapor would have a much harder time condensing into the kind of clouds capable of producing rain. But because the troposphere holds such an abundance of both moisture and airborne particles, it creates ideal conditions for clouds to form, gather, and eventually release their rain back to the surface below. It's a quiet, layered process, isn't it? Dust rising gently from the ground. Water vapor drifting invisibly through the air. The two coming together, high above us, forming the clouds that will eventually darken, gather weight, and release rain back toward the Earth they originally came from, a slow, continuous cycle, unfolding endlessly within this single, dense, ever-changing layer of sky. So as we bring this section of our journey to its quiet close, take a moment to imagine the troposphere in its entirety, thick with air, heavy with moisture, restless with constant change, thinning gently near the poles and stretching higher above the warmth of the equator, holding within it nearly all of the atmosphere's mass, nearly all of its weather, nearly all of the clouds and rain that shape life across the surface of our planet. It is, in many ways, the most intimate layer of our atmosphere, the one closest to us, the one most directly shaping our daily experience of the world, even as far quieter, far more distant layers continue their own patient work high above. In the next part of our journey, we'll continue rising gently through this remarkable shield, uncovering even more quiet wonders hidden within the layers of sky stretching endlessly above us. For now, rest here a little longer, beneath this dense, ever-changing layer of air, where weather is born, where clouds gather quietly overhead, and where the gentle rhythm of change continues, night after night, high above the stillness of your rest. Before we move on, let's stay with the troposphere for just one more moment. There is something happening within it that helps explain much of the weather behavior we've already discussed, the way it grows colder the higher you travel. As you rise through the troposphere, away from the warmth of the surface, the temperature steadily drops. This might seem a little counterintuitive at first. After all, you might expect to feel closer to the sun, and therefore warmer, the higher you climb. But the truth is quite different. The surface of the Earth absorbs sunlight and radiates that warmth back upward, heating the air closest to it most directly. As you move further from that surface, that warming influence weakens, and temperatures grow steadily colder. This gradual cooling with altitude plays an important role in shaping the very clouds and storms we spoke of earlier. Warm air near the surface rises, and as it climbs higher into the increasingly colder air above, it cools rapidly, causing the moisture within it to condense into clouds. In more dramatic cases, this same process, warm air rising quickly into much colder air above, can fuel the kind of powerful, towering storm clouds capable of producing thunder, lightning, and heavy rainfall. It's a quiet kind of cause and effect happening constantly above us. Warmth rising, cold air waiting above, moisture condensing somewhere in between. And from that simple temperature difference, entire storm systems are born. But once you rise beyond the troposphere, into the layer we touched on earlier, something rather unexpected begins to happen. The temperature pattern reverses entirely. This next layer is the stratosphere, and it holds within it something we've already spent time exploring, the ozone layer. It's worth returning to this for a moment, because the presence of ozone here isn't just a passing detail. It's one of the primary reasons the stratosphere holds such significance for life on Earth. This is the layer responsible for absorbing much of the sun's harmful ultraviolet radiation, offering the kind of quiet, essential protection we spoke about earlier in our journey. And it's precisely because of this ozone that something rather unusual happens to temperature within the stratosphere. Unlike the troposphere below it, where temperatures grow colder with altitude, the stratosphere behaves in the opposite way. As you rise higher within this layer, temperatures actually begin to increase. This happens because ozone absorbs solar energy, specifically the ultraviolet radiation we've discussed. As ozone captures this energy, it releases some of it as heat, gradually warming the surrounding air. And because ozone becomes more concentrated at higher altitudes within the stratosphere, the warming effect grows stronger the further you travel upward, creating a layer where temperature rises rather than falls with height. It's a rather elegant kind of reversal, isn't it? Just as we grow accustomed to the idea that height brings cold, this remarkable layer quietly defies that expectation, warming instead, gently, as it climbs higher and higher above the Earth. This unusual temperature pattern, rising steadily with altitude, stands in direct contrast to the layer below it. Where the troposphere grows colder the higher you travel, the stratosphere does precisely the opposite, growing warmer the further it stretches from the surface. This difference isn't just an interesting detail about temperature. It has real, practical consequences for the way air behaves within each layer. Because the stratosphere warms with altitude rather than cooling, the air within it becomes remarkably stable. Warmer air resting above cooler air tends to stay in place, rather than rising and mixing the way it does within the more turbulent troposphere below. This stability means the stratosphere experiences far less of the constant churning, rising, and mixing that defines weather patterns closer to the surface. This is part of why the stratosphere feels like such a different world compared to the layer beneath it. Where the troposphere is restless, shifting, and constantly reshaping itself with clouds and storms, the stratosphere remains comparatively calm, steady, quiet, and largely undisturbed by the turbulence unfolding far below. And this remarkable stability is precisely why the stratosphere has become such a valuable region for something deeply familiar to many of us: high-altitude flight. Commercial aircraft often cruise within the lower reaches of the stratosphere, precisely because the air there tends to be so much smoother than the air closer to the surface. Because this layer experiences far less turbulence, far less mixing, and far more stability than the troposphere below, it offers an ideal environment for long, steady flights. This is part of why airplane journeys often feel calmer once a plane has climbed to its cruising altitude. Down closer to the surface, within the turbulent troposphere, aircraft can experience bumps, shifts, and sudden changes caused by rising warm air, storms, and shifting winds. But once a plane rises into the stable air of the stratosphere, much of that turbulence fades away, replaced by long stretches of smooth, steady travel. It's a small, quiet reminder that even something as ordinary as an airplane ride connects us, in its own way, to the deeper structure of our atmosphere, to layers of air with entirely different personalities, entirely different behaviors, existing just beyond what we can see from a window seat high above the clouds. Now, let's continue rising, beyond the stratosphere, into a layer we've mentioned briefly before, the mesosphere. It's here that we find something truly extreme, the coldest temperatures found anywhere within Earth's atmosphere. Near the very top of the mesosphere, temperatures can plunge to around 90 degrees below 0 Celsius. It's difficult to fully imagine cold on that scale, colder than nearly anywhere on Earth's surface, colder than the harshest polar winters, colder than almost anything most of us will ever personally experience. This extreme cold exists here for a particular reason. The mesosphere sits above the warming influence of the ozone layer, yet it hasn't yet reached the layer above it, where different atmospheric processes create their own kind of heat. Caught between these two very different regions, the mesosphere becomes the coldest point within the entire atmosphere, a quiet, frozen boundary drifting high above the Earth. It's worth pausing here, just to imagine it. A place so remote, so distant from the surface, that its temperatures plunge far beyond anything experienced by any living creature on the ground below, an invisible, frozen layer, existing quietly above the clouds, above the stratosphere, above nearly everything we associate with sky. And yet, just beyond this frozen boundary, the atmosphere transforms once again, this time, in the opposite direction entirely. Beyond the mesosphere lies the thermosphere, the layer we touched on earlier as one that absorbs high-energy radiation from the sun. And here, temperatures don't just rise gently, the way they do within the stratosphere. They rise dramatically, reaching levels that sound almost impossible to believe. Within the thermosphere, temperatures can climb as high as 2,000 degrees Celsius. It's an extraordinary contrast, isn't it? Moving from the coldest point in the entire atmosphere, within the mesosphere, into a layer capable of reaching temperatures hot enough to melt nearly any material we might imagine. This intense heat exists because the thermosphere absorbs an enormous amount of solar radiation, particularly the high-energy X-rays and ultraviolet rays we discussed earlier. As this radiation is absorbed, it energizes the few particles present within this extremely thin layer of atmosphere, causing temperatures to rise to these remarkable extremes. And yet, despite these seemingly unbearable temperatures, this heat wouldn't feel the way we might expect if we were somehow able to stand within it. Because the air within the thermosphere is so incredibly thin, so sparse, there simply aren't enough particles present to transfer that heat the way denser air would closer to the surface. It's a strange, almost paradoxical truth, a layer capable of reaching temperatures far hotter than any furnace, and yet, physically, it wouldn't feel like heat at all, in the way we typically understand it. There is something almost dreamlike about this entire journey through temperature, isn't there? Beginning within the restless troposphere, where warmth near the surface gives way to cold with altitude. Rising into the surprisingly warm stratosphere, protected and stabilized by ozone. Passing through the freezing extremes of the mesosphere. And finally arriving within the blazing, yet strangely gentle, thermosphere, each layer telling its own quiet story through nothing more than the rise and fall of temperature. It's a reminder of just how varied, how complex, how quietly extraordinary this invisible shield truly is. Not a single, uniform layer of air, but a series of distinct worlds, stacked one above another, each shaped by its own delicate balance of energy, distance, and light. In the next part of our journey, we'll continue exploring even more of these remarkable qualities, moving further into the story of Earth's atmosphere and the quiet, protective forces shaping it high above us. For now, let yourself rest here a while longer, drifting gently between warmth and cold, stability and turbulence, closeness and distance, beneath a sky far more intricate, far more remarkable than most of us ever pause to imagine. We left off within the thermosphere, that strange layer of extreme heat and thin, sparse air. But it's within this very same layer that something far more beautiful takes shape, something many of us have seen, or dreamed of seeing, glowing softly across a night sky. The aurora. Auroras form when charged particles, carried on solar wind from the sun, collide with gases high within the thermosphere. As these particles strike atoms of oxygen and nitrogen, they release small bursts of energy in the form of light, shimmering greens, soft pinks, gentle purples, drifting and rippling silently across the sky like something almost otherworldly. It's remarkable to think that this same layer, capable of reaching temperatures near 2000 degrees, is also responsible for some of the most delicate, breathtaking light shows visible from Earth's surface. A place of such intensity, quietly producing something so soft, so graceful, so seemingly gentle to behold. And these glowing lights aren't just beautiful. They're also a visible reminder of something much larger, the ongoing relationship between Earth's atmosphere and the constant stream of energy arriving from space. This is what scientists often refer to as space weather, the invisible, ever-present exchange between the sun's energy and our planet's protective shield. Auroras are simply the visible surface of that exchange, the atmosphere quietly absorbing, redirecting, and transforming energetic particles arriving from millions of kilometers away, and in doing so, creating one of nature's most breathtaking displays. It's a beautiful thought to hold on to, isn't it? That the same atmosphere responsible for filtering danger and holding warmth in place is also capable of producing something so purely wondrous, a quiet reminder that protection and beauty aren't always separate things. Within this same region of the atmosphere, another quiet, invisible process is unfolding as well, one that shapes something many of us rely on without ever thinking about it. The ionosphere. The ionosphere isn't a separate layer in the same way the troposphere or stratosphere are. Instead, it's a region that overlaps with parts of the mesosphere and thermosphere, defined not by temperature, but by a particular kind of activity happening within it. Here, solar radiation strikes atoms and molecules with enough energy to knock electrons loose from them, creating what are known as charged particles, or ions. This process, called ionization, gives the ionosphere its name and its unique electrical properties. These charged particles have a rather practical effect. They interact with radio waves, allowing certain signals to bounce and travel much further than they otherwise could along the curved surface of the Earth. In a quiet way, this invisible, electrically active region high above us plays a role in something as ordinary and familiar as long-distance radio communication, connecting voices, signals, and information across vast distances, thanks to a layer of atmosphere most of us will never see or think about directly. Now, somewhere within this same general region, high above the mesosphere, lies a particular marker that has become widely recognized, a symbolic boundary between our atmosphere and the beginning of outer space. This is known as the Kármán line, and it rests within the thermosphere, at an altitude of approximately 100 kilometers above the surface. While we've already discussed how Earth's atmosphere doesn't truly end at any single, sharp boundary, the Kármán line offers something useful nonetheless, a commonly accepted reference point, a line drawn not because the atmosphere abruptly stops there, but because it marks a useful threshold, often used to define where space is considered to officially begin. It's a fascinating middle ground, isn't it? A boundary that exists more as a shared agreement than a physical wall, a quiet reminder that even as scientists search for clarity, some parts of nature simply resist being divided into neat, definitive lines. Beyond the Kármán line, beyond the thermosphere itself, we eventually arrive once more at the layer we touched upon at the very beginning of our journey, the exosphere. This is the outermost layer of Earth's atmosphere, the final, faint stretch before the true emptiness of space begins. And it's here that something quite different happens compared to every other layer we've explored so far. Within the exosphere, gas molecules are spread so thin, so far apart from one another, that they behave less like a connected layer of air, and more like scattered, individual particles drifting through near emptiness. Some of these particles move quickly enough, and are positioned loosely enough by gravity, that they eventually drift entirely away from Earth, escaping gradually into the vast openness of space. It's an almost delicate image, isn't it? The very outer edge of our planet's protective shield, thinning so gradually, so gently, that individual molecules simply drift away, one by one, disappearing quietly into the darkness beyond. And yet, despite this slow, continuous loss of gas particles, Earth's atmosphere as a whole remains remarkably stable. This gradual leakage happens at such an incredibly slow rate that it poses no real threat to the atmosphere's overall balance. Over the vast span of Earth's history, this quiet, ongoing process has continued steadily, without ever disrupting the delicate equilibrium that allows life to flourish here. It's a comforting thought, in its own way. Even as tiny fragments of atmosphere drift silently into space, day after day, year after year, the greater whole remains steady, protected, in part, by the same gravity that has held this shield in place since the very beginning of our planet's story. This gradual thinning of gas within the exosphere is closely connected to something else we experience much closer to home: atmospheric pressure. As altitude increases, atmospheric pressure steadily decreases. Down here, near the surface, the weight of the entire atmosphere above us presses downward, creating a relatively high level of pressure. But as you climb higher, whether ascending a mountain or rising through the layers of atmosphere themselves, there is simply less air above you, and therefore, less pressure pressing down. This is why high mountain air feels so noticeably thin. With less atmospheric pressure at higher elevations, fewer oxygen molecules are packed into every breath, making it harder to breathe comfortably the higher one climbs. Mountain climbers ascending extreme peaks often need supplemental oxygen for precisely this reason, not because oxygen disappears entirely, but because there simply isn't enough atmospheric pressure remaining to deliver it efficiently to the body. And this relationship between altitude and pressure doesn't only affect climbers and travelers. It also plays a significant role in shaping weather patterns across the globe. Differences in atmospheric pressure, both across various altitudes and across different regions of the Earth's surface, help drive the movement of air itself. Areas of high pressure and low pressure interact constantly, creating winds, storms, and shifting weather systems that circulate across the planet. This invisible dance of pressure, rising and falling gently across the surface of the Earth, is part of what gives our atmosphere its restless, ever-changing character. So as we bring this stretch of our journey to its quiet close, take a moment to imagine everything unfolding above us at this very moment. Charged particles colliding softly within the thermosphere, painting the sky with light. Electrons quietly dislodged within the ionosphere, allowing distant signals to travel further than they otherwise could. A faint, symbolic line marking the edge of space, 100 kilometers above the ground. Gas molecules drifting gently away within the exosphere, thinning so gradually that the atmosphere remains stable despite this constant, quiet loss. An atmospheric pressure, shifting gently with every change in altitude, shaping both the air we breathe and the weather unfolding across the surface of our world. Layer upon layer, process upon process, each one distinct, each one quietly essential, weaving together into something vast, intricate, and endlessly protective. In the next part of our journey, we'll continue drifting through the remaining wonders of this remarkable shield, uncovering even more of the quiet forces shaping the sky above us. For now, rest here a little longer, beneath a sky glowing softly with unseen energy, beneath a boundary drawn gently at the edge of space, beneath an atmosphere thinning slowly, patiently, into the quiet vastness beyond. We spoke, just before, about how thinner air at higher altitudes makes breathing more difficult. It's worth sitting with that idea a little longer, because it connects to something deeply physical about the way our bodies interact with the atmosphere surrounding us. At higher elevations, where atmospheric pressure has noticeably dropped, both humans and animals begin to feel the effects rather quickly. With fewer oxygen molecules available in every breath, the body has to work harder simply to gather the oxygen it needs. This is why even simple movements, like walking uphill, can feel far more exhausting at high altitudes than they would at sea level. The air hasn't changed in composition. It's simply thinner, more spread out, offering less oxygen with every inhale. Many animals native to high-altitude regions have adapted over generations to cope with this thinner air, developing larger lungs, or blood better suited to carrying oxygen efficiently. But for those of us unaccustomed to such heights, the difference can be felt almost immediately, a quiet reminder of just how much we depend on the density of air closer to the surface, without ever needing to think about it. This entire relationship between altitude and breathing brings us back to something we touched on earlier, but haven't yet fully explored: the actual weight of the atmosphere itself. It might seem strange to think of air as something with weight. After all, it feels invisible, weightless, easy to move through without any resistance at all. And yet, air is made of countless molecules, each one contributing, however slightly, to an enormous cumulative weight pressing down upon the surface of our planet. At sea level, this weight creates a measurable amount of pressure, approximately 14.7 pounds pressing down on every single square inch of the Earth's surface. It's a rather astonishing number when you truly consider it. Every square inch of your body, standing here at sea level, is constantly experiencing this quiet, unnoticed pressure from the atmosphere surrounding you. We don't feel this pressure directly, largely because our bodies have evolved within it, adapted to it so completely that it simply feels like nothing at all. Like silence. Like stillness. And yet, it's there, every moment, a subtle reminder of just how substantial our seemingly weightless atmosphere truly is. This same figure, 14.7 pounds per square inch, represents the baseline pressure most of us experience without ever noticing, so long as we remain close to sea level. But as we discussed only moments ago, this pressure doesn't remain constant as altitude increases. The higher you travel, whether up a mountain or through the layers of atmosphere themselves, the less air remains above you, and therefore, the lower the surrounding pressure becomes. This steady decrease in pressure is part of why breathing becomes more difficult at higher elevations, less atmospheric weight pressing down, and therefore, fewer oxygen molecules delivered with each breath. It's a quiet, elegant relationship, isn't it? Weight and pressure and breath, all connected, all shaped by the simple, invisible presence of the air surrounding us. And this same idea, that air as real, physical weight, applies once again as we consider where this weight originates in the first place. The atmosphere's pressure exists precisely because air possesses mass. Every molecule of nitrogen, oxygen, and trace gas we discussed earlier carries a small amount of weight, and when combined across the entire depth of the atmosphere, that weight becomes substantial enough to create the pressure we experience at the surface. It's easy to forget, surrounded by something so seemingly weightless, that the very air around us carries real physical presence, pressing down gently, continuously, in every direction. Now, let's shift our attention to something shaped, in part, by this pressure and density we've been discussing, a phenomenon high above us that quietly influences weather patterns across the entire globe. The jet stream. The atmosphere doesn't just sit passively above us. It moves in complex, powerful patterns, and one of its most significant movements occurs high above the surface, in narrow, fast-moving currents of air we call jet streams. These jet streams form near the boundary between the troposphere and the stratosphere, the very layers we explored earlier, where temperature differences create powerful currents of moving air. And their influence stretches far beyond their own narrow pathways, helping to steer larger weather systems across vast distances, shaping storms, temperature shifts, and precipitation patterns across entire continents. It's remarkable to imagine a narrow, high-altitude current of air, invisible from the ground, quietly guiding the movement of weather systems experienced by millions of people below, who likely never think about the powerful, distant force shaping the skies above them. And these jet streams aren't gentle, meandering currents. They move with extraordinary speed. Jet streams are often described as rivers of air, flowing high above the Earth's surface, and much like rivers, they follow winding, shifting paths across the globe. But unlike the rivers we're familiar with on the ground, these atmospheric rivers can move remarkably fast, sometimes exceeding 200 miles per hour. It's a rather astonishing image, isn't it? High above us, far beyond what we can see or feel from the ground, powerful rivers of wind rush across the sky, moving faster than almost anything we experience directly in our daily lives, shaping storms, influencing seasons, and quietly directing much of the weather unfolding beneath them. These same fast-moving currents also have a very practical influence on something many of us have personally experienced: air travel. Airlines often plan flight paths with jet streams in mind, taking advantage of these powerful currents to reduce flight times when traveling in the same direction as the stream, or adjusting routes to avoid unnecessary delays when flying against it. A flight traveling eastward, aligned with the natural direction of a jet stream, can often arrive significantly faster than the same journey made in reverse, simply because of the powerful assistance, or resistance, offered by these high-altitude currents of air. It's a quiet reminder of just how deeply connected our daily lives are to forces moving invisibly, far above us, shaping not just the weather we experience, but even the pace of our own travels across the world. And finally, let's turn to something perhaps unexpected within our exploration of the atmosphere: sound itself. We often think of sound as something separate from the physical world around us, something abstract, intangible. But sound, in truth, depends entirely on the presence of a physical medium to travel through, and here on Earth, that medium is air. As sound waves move through the atmosphere, they travel at a measurable, consistent speed, one that can be calculated with remarkable precision. At sea level, sound travels through air at approximately 767 miles per hour. This is the speed we often refer to as the sound barrier, the threshold associated with sonic booms, when an object moves fast enough to outpace the very sound waves it generates. But this speed isn't fixed. It shifts depending on temperature and air density, both of which change with altitude and atmospheric conditions. In colder, thinner air, sound tends to travel slightly slower. In warmer, denser air, it can travel a little faster. It's yet another quiet example of how deeply interconnected the atmosphere's properties truly are: temperature, density, and even the speed of sound itself, all shaped by the same delicate balance of gases surrounding our planet. There's something quietly beautiful in that thought, isn't there? That even something as intangible as sound, every whispered word, every distant rumble of thunder, every soft breath moving through the air right now, is entirely dependent on the presence of this atmosphere we've been exploring together. Without it, sound simply wouldn't exist at all. Only silence, the true, absolute silence of empty space. So as we gather together everything explored in this section of our journey, take a moment to imagine the full weight, the full motion, the full presence of the atmosphere surrounding you right now. Thin air struggling to sustain breath at great heights. The quiet, constant pressure of 14.7 pounds pressing gently against every inch of your body. Powerful rivers of wind, racing invisibly across the sky, shaping weather and travel alike. And sound itself, carried gently through the air, allowing every voice, every whisper, every quiet moment of connection to exist at all. All of it, weight, pressure, wind, and sound, woven quietly together within this single, remarkable shield surrounding our planet. In the next part of our journey, we'll continue drifting through even more remarkable qualities of this atmosphere, uncovering further wonders hidden within the sky stretching endlessly above us. For now, rest here a little longer, beneath a sky filled with invisible weight, distant rivers of wind, and the quiet, ever-present hum of sound moving gently through the air around you. We spoke, just before, about the speed of sound, and the way it moves through the atmosphere surrounding us. There's one more piece to that story, one final thought connected to what happens when something moves faster than sound itself. When an aircraft accelerates beyond the speed of sound, it begins to outrun the very sound waves it produces. As it does, those compressed waves gather together, building into a powerful pressure wave that releases suddenly, all at once, creating the sharp, thunderous sound we know as a sonic boom. It's a striking phenomenon, isn't it? A single moment where something physical, something man-made, briefly outpaces one of the most fundamental properties of the air itself, and in doing so, creates a sound loud enough to be heard, sometimes felt, across the ground far below. This is precisely what happens with supersonic aircraft, designed specifically to travel faster than the speed of sound within our atmosphere. As they cross that particular threshold, they leave behind them this same distinctive boom, a brief, powerful reminder of just how deeply our experience of speed, sound, and motion remains tied to the atmosphere surrounding our planet. Now, let's turn to something far gentler, something many of us have looked up and noticed without ever fully understanding why it appears the way it does. The blue color of the sky above us. Sunlight, though it appears white or pale yellow to our eyes, actually contains a full spectrum of colors, blended together. As this light travels through Earth's atmosphere, it encounters countless tiny molecules of gas, and as it does, something quietly remarkable happens. The light begins to scatter. Different colors of light travel in different wavelengths, and shorter wavelengths, like blue and violet, tend to scatter far more easily than longer wavelengths, like red or orange. Because blue light scatters so much more readily as it moves through the atmosphere, it spreads across the entire sky, reaching our eyes from every direction we look, rather than only from the direction of the sun itself. This is why, on a clear day, the sky above us appears to glow in soft, endless blue, not because the atmosphere itself is blue, but because of the quiet, invisible way sunlight interacts with the very molecules that make up the air surrounding our planet. It's a beautiful thought to rest in, isn't it? That every gentle blue sky you've ever looked up at, every quiet afternoon spent beneath open air, was made possible by nothing more than sunlight scattering softly through the same invisible shield we've been exploring together this entire journey. High above that same blue sky, far beyond where clouds typically form, there exists something rarer, something far more elusive. Noctilucent clouds. These faint, delicate clouds form incredibly high within the upper atmosphere, so high that they remain illuminated by sunlight even after the sun has set below the horizon for those of us on the ground. This creates a soft, glowing, almost silvery blue appearance, visible only under very particular conditions, typically during twilight hours in certain regions of the world. Because of their rarity, and their delicate, glowing appearance, noctilucent clouds are sometimes described as night-shining clouds, a quiet, beautiful reminder that even in the furthest reaches of our atmosphere, moments of unexpected beauty continue to unfold, largely unseen by most of the world below. And within this same upper region of the atmosphere, another quiet, powerful force continues its own steady work. Earth's magnetosphere. The magnetosphere exists at the boundary between our atmosphere and the wider reaches of space, shaped by the planet's magnetic field. It plays a crucial role in interacting with charged particles arriving from the sun, deflecting much of this energy away from the Earth, and in doing so, helping protect the delicate balance of gases within our atmosphere from being stripped away entirely. It's worth remembering, as we near the end of this journey together, just how many quiet, interconnected systems have been working simultaneously to protect and sustain life here. The atmosphere itself, layer upon layer. And beyond it, this final, invisible boundary, the magnetosphere, standing as one more silent guardian, shielding our planet from the harsher realities of space. And as we reflect on everything we've explored throughout this journey, it becomes clear that one quiet thread has connected nearly every layer, every process, every remarkable feature we've discussed: the way temperature changes so differently within each part of the atmosphere. We've traveled through the troposphere, where temperatures grow colder with height, into the stratosphere, where temperatures rise again, warmed gently by ozone, through the freezing extremes of the mesosphere, and finally, into the intense, if strangely gentle, heat of the thermosphere. Each of these temperature patterns, distinct and different from one another, helps define the very structure of our atmosphere, creating the layered, complex shield that has protected life on Earth for countless generations. This ever-changing relationship between altitude and temperature isn't simply an interesting detail. It's part of what allows each layer to serve its own particular purpose, trapping warmth near the surface, absorbing radiation high above, burning away debris in the quiet stillness of the mesosphere, and interacting with the energy of the sun itself within the thermosphere. Layer by layer, temperature by temperature, this entire structure works together, creating a stable, livable environment for the world beneath it. And this idea, this quiet importance of balance and protection, brings us to one final thought, one that feels especially fitting as we come to the close of this long, gentle journey together. Earlier in our exploration, we spoke of the ozone layer and its vital role in absorbing the sun's harmful ultraviolet radiation. For a period of time, this same protective layer faced a serious challenge, particularly above Antarctica, where a significant thinning, often referred to as the ozone hole, began to form. This thinning was caused primarily by certain man-made chemicals, known as chlorofluorocarbons, which gradually made their way into the atmosphere and began breaking down the delicate ozone layer high above the Earth's surface. But in a rare and hopeful turn, the world responded. Nations came together, recognizing the importance of this protective layer, and gradually phased out the use of these harmful chemicals. And slowly, patiently, over the years that followed, the ozone hole above Antarctica has begun to shrink, healing gradually as the atmosphere continues its own quiet process of restoration. It's a rather beautiful note to end on, isn't it? A reminder that this vast, ancient, endlessly protective shield surrounding our planet isn't only something to admire from a distance. It's something we remain connected to, something capable of being affected by our choices, and in this particular case, something capable of healing when given the chance to do so. And so, as we come to the end of this long, quiet journey together, let's take one final moment to look back at everything we've explored. We began with a thin, invisible blanket of gas, wrapped gently around our planet by nothing more than the quiet pull of gravity. We traveled upward through layer after layer, each one distinct, each one essential, the restless troposphere, alive with weather and change. The stable, protective stratosphere, warmed by ozone, and helping to shield us from ultraviolet light. The freezing stillness of the mesosphere, where meteors quietly burn away. The intense, radiant thermosphere, where auroras shimmer and charged particles dance across the sky. And finally, the fading, whispering edge of the exosphere, where our atmosphere gently releases its hold, and space begins. Along the way, We discovered the quiet chemistry of the air we breathe: nitrogen and oxygen, water vapor and trace gases, each playing its own small but essential role. We explored the weight of the atmosphere pressing gently against us, the rivers of wind flowing far above our heads, and the sound waves carrying every whispered word through the air around us. We witnessed the sky turn blue through nothing more than scattered light, and glimpsed rare clouds glowing softly at the edge of night. And we came to understand just how deeply this vast, invisible shield continues to protect every living thing beneath it, quietly, faithfully, moment after moment, breath after breath. This has been the story of Earth's invisible shield, a story stretching from the ground beneath your feet, all the way out into the quiet vastness of space. A story of protection, and balance, and quiet, patient resilience. And now, as this journey comes to its gentle close, let yourself rest here a little longer, beneath a sky far more remarkable than most of us ever pause to consider, held safely, quietly, endlessly, within the gentle embrace of the atmosphere above. Rest now, and let the sky watch over you, just as it always has.